Welcome back to Analog Circuits. Today is lecture 28 and we are going to discuss the Cascode and the Cascade amplifier. It is actually going to be a revisit of what we had done long back, and this time we are going to revisit it with capacitance in mind. So, in the last class last two classes actually we had done the common source amplifier, the common drain amplifier, the common gate amplifier with capacitance effects taken into account. We saw that the common source amplifier gave us one pole in the left half plane and 1 0 in the right half plane. The common gate amplifier gave us only one pole, no zeros, and the common drain circuit gave us a pole as well as a 0, right. It gave us a pole as well as a 0. The 0 was thankfully in the left half plane, the pole was also in the left half plane. We further examined the common drain amplifier output impedance, re-examined. We said that the common drain amplifier is going to be used in a situation where the source impedance is large, and we applied a source impedance and re-examined the output impedance of the common drain amplifier and found that it is inductive in nature. Even though there is no inductor inside in the circuit, there is no inductor at all. However, when you look into the output of the common drain amplifier, it behaves as if it was an inductor. Okay. So, this is the stuff that we have seen so far. Next on the agenda is to see multi-transistor circuits, and our two important multi-transistor circuits are the Cascode amplifier as well as the cascade of two common source amplifiers. The Cascode is also two amplifiers, a common source followed by a common gate. Okay. Common source followed by common gate is called Cascode, and then we will do the common source followed by common source as well. So, this is the overall outline of today's lecture. So, we are going to start with the Cascode amplifier, and the Cascode amplifier has to be analyzed with a current source on the top. If you do not put a current source, if you only put a resistor, then it is unreasonable. Okay. Ideally, what you want is a cascode of NMOS devices as well as a cascode of PMOS devices. If you do not want to draw the cascode of the PMOS devices right away, then at least place a current source over there. Do not place a resistor, because that just kills, that just destroys the purpose of the cascode. The purpose of the cascode is to get a very large output impedance. Okay. So, this is the Cascode circuit. It is a common source amplifier followed by a common gate amplifier. Okay. The common source amplifier is a voltage controlled current source. The common gate amplifier is a current controlled current source. Okay. So, its input is a current and the overall output is an even better current source than that of the common source amplifier. Okay. That is the idea. If I look at the output impedance, so the way we analyze this is, first we always analyze DC, then we place the capacitors, we find the poles and zeros, and then we write out the transfer function. That has been the strategy so far. Okay. So, let us try to do that. Of course, this is going to be a situation where that precise strategy is not going to work. You will need to, you will need to be a little more flexible about it. So, first we are going to analyze DC. DC analysis involves two things. One is output impedance, the other is short circuit current. Okay. So, If I look at the output impedance at DC, it is straightforward. It is an application of our formula. First of all, you have to apply 0 volts at the input. So, as soon as you have applied 0 volts at the input, this MOSFET now contains GM is gone, GMB was gone anyway, only RDS. So, this MOSFET M1 has only RDS on it, and now you apply the formula. The formula is very straightforward, right. Looking into the drain of M2, the impedance that you are going to see is equal to intrinsic gain of M2, which is GM plus GMB times RDS2, that is the intrinsic gain of M2, times what is on the drain, what is on the source, which is RDS1 plus RDS1 plus RDS2. All right, this is the result. This was the formula. Done. Output impedance is done. See, by now you would have realized that those two formulae are very important. Okay. If you want to make any headway in this course, if you still have not memorized those two formulae, do memorize, because they are vital for this course. Okay. Next, we are going to use the find out the short circuit transconductance. Now, for the short circuit transconductance, what am I going to do? I am going to connect this output to a ground, all right, and you do not have to draw all of this all the time. Imagine that you have connected this to ground, and we are now going to measure the current in that short circuit. So, first of all of this on top does not matter. Okay. I apply an input over here, V in, let us say I have applied V in over here. M1 is going to respond with its GM, right. So, it is going to create a current GM times V in, GM1 times V in inside. GMB is not required because body is at 0 volts. Yeah. So, GM times V in current is created over here through M1. Now, this current sees RDS 1, which I have not drawn, and it also sees an impedance looking into the source of M2. Okay. The current now has to distribute itself between these two impedances. One is RDS of M1, which I am not drawing, and the other is whatever you are looking up into the source of M2. What do you see looking up into the source of M2? It is 1 by GM2 in parallel with RDS2, okay, or you can apply your formula, the second formula, right, and say that drain is terminated with 0 ohms, right, with a short circuit. So, RD is equal to 0, and that second formula was RD plus RDS divided by 1 plus GM intrinsic gain, GM plus GMB times RDS, that is what it was. Okay, so, that is the impedance that you will see. Looking into the source of M2, you will see an impedance RDS2 plus RD, which is 0, divided by 1 plus GM2 plus GMB2 times RDS2. This is what you see looking into the source of M2. Once again, I apply V in over here. M1 responds with a current GM times V in, GM1 times V in. This current has to choose between two paths. One path is RDS1 to ground, the other path is this impedance to ground. Okay, this is ground anyway, right? This is between this and ground. Okay, so this current has to share, and how does current share? You know the current sharing relationship, right? I goes, current I comes, it faces two resistors R1, R2. The current in R1 will be proportional to R2 divided by R1 plus R2. Okay. So, the current going into the source of M2 is going to be equal to RDS1 divided by RDS1 plus so much, this fraction of GM1 V in, right. V in times GM1 was the current that was created. I am not writing V in. GM1 times V in was the current created. That current had to share between RDS1 and this impedance looking into the source of MOSFET number 2, right. This is the current sharing relationship, right. R1 divided by R1 plus R2 is the current going into R2. Okay. This entire current is going to now go into the short circuit, right. Whatever current came, that entire current will now go into the short circuit. So, this is my short circuit transconductance. Okay. And see, I am writing this huge massive expression just by inspection. Okay. We did not do KVL, we did not do KCL, we are not doing anything. We just memorized those two formulae, right. We did not even expand the circuit, right. We are just looking at the circuit, talking and writing the expression. Okay. So, that is how you need to do it. The more KVLs and KCLs you write, the less the less understanding you will get, the less intuition you will develop. Now, what is the intuition here? The intuition is that this quantity, okay, this second quantity is small. Why? Because 1 plus the intrinsic gain is more or less equal to the intrinsic gain. Intrinsic gain of a MOSFET, hopefully you have biased the MOSFET well, right, correctly. Hopefully you have got, you are in the flat region of the MOSFET, which means that the intrinsic gain of the MOSFET is some large number 20, 40, 50, right, something, and therefore 1 plus that intrinsic gain should therefore be more or less equal to the intrinsic gain, which means you can ignore the 1. Now, RDS2 cancels out, okay, and therefore, this entire thing is just 1 by GM2 plus GMB2, right. Transconductance of the second MOSFET is hopefully larger than 1 by RDS1, or in other words, RDS1 should be much larger than 1 by the transconductance. Okay. In other words, this entire term is going to be more or less close to 0 compared to RDS1, which means that this entire fraction is more or less equal to 1. This fraction is 1, and therefore, the transconductance is just GM1. Okay. So, that is how the cascode operates. You create a current over here, and the second cascoding transistor takes all that current and makes a current source of it, right. So, I created a current with M1, and this second common gate circuit took that current and made it into a current source. That is the idea of the cascode, right. So, M2 made it into a current source, and therefore, the transconductance is just GM1. That is the intuition. So, I have got GM1 as the transconductance, and my R out is some large impedance because it is a current source, right. Once again, R out is large because of this first term. The first term is large over here, the second and third terms do not matter. You have got intrinsic gain times RDS1, obviously that is going to be much larger than RDS1 and RDS2. So, the first term is the dominant term in the output impedance, and therefore, once you have the transconductance GM1 and the output impedance, you can write out the voltage gain. If you want to write out the voltage gain, it is the product of the transconductance and the output impedance. So, GM1 times this first term, GM1 times RDS1 times GM2 plus GMB2 in times RDS2. So, intrinsic gain of the first device times intrinsic gain of the second device, that is approximately your overall voltage gain. All right, this is DC. Now, our job is to throw in the capacitors. And what do we do? What all capacitors do we have? We now have two devices. So, we have to discuss 2 into 4 8 capacitors. First, we have CGS 1. Fine. Then we have C source to body of 1, which is irrelevant because source is at ground, body is also at ground. So, no current goes through it anyway, will not draw it. Next, we have C gate to drain of 1, and next we have C drain to body of 1. Okay, so that is 4 capacitors for MOSFET number 1. Then let us talk about MOSFET number 2. We have C gate to source of MOSFET number 2. Now, C gate to source is between source and ground, okay, and we had a similar capacitor over here. So, it just adds on to this. Next, we had C gate to drain of MOSFET number 2. All right. Then we have C drain to body of MOSFET number 2 between drain and body, and that just adds up with CGD2. And lastly, we have C source to body of MOSFET number 2. Source to body, body is at ground, and we have a similar capacitor over here. So, it adds up. Is this okay? All right, great. So, these are all the capacitors. Now, instead of writing these complicated expressions, I am going to simplify a bit. Okay, I do not like these complicated expressions. I am going to redraw my circuit in this fashion. So, let us call this node 1, let us call this node 2, and let us call this node 3. Okay. So, I have a capacitor between node number 3 and ground, which is actually CDB2 plus CGD2. I am going to call it C3. I have a capacitor between node number 2 and ground, which is actually CDB1 plus CGS2 plus CSB2. I am going to call it C2. I have a capacitor between node number 1 and ground, which is CGS1. I am going to call it C1. And I have one last capacitor between nodes 1 and 2. I am going to call it C12. It is actually CGD1. Okay. So, what you are going to notice, by the way, is that this gate to drain capacitance is very annoying. This one, this C12 is very annoying. Okay. You are going to see this, you have already seen this before. it created a right half plane 0 in the common source amplifier, right. This gate to drain capacitance is going to create trouble, we do not like it, all right. If you ever get into device design, right, if you get into device physics, you will see that a lot of effort is put into reducing the gate to drain capacitance, we do not like it. Okay. The good news is that the device design guys are not doing a bad job. Okay. When the MOSFET pinches off, beyond pinch off, see gate to drain actually goes all the way down, it goes becomes smaller and smaller, right. So, they are not doing a bad job, they are doing a good job. So, C12 over here is actually a small capacitance, it is the smallest of the lot. However, even small capacitances are annoying, right. Just this location, this the place where it is, you know, everything else is with respect to ground, this capacitance is floating in between two nodes, it creates, you know, misery, all right. So, we are going to see some, you know, approximations later on how to deal with this gate to drain capacitor, how to deal with capacitors that are floating around. We will do these approximations later on, but for now let us try to analyze this particular circuit. Okay. This is my output. I already have the DC expressions. Now, what do I have to do? I have to do my same two experiments. One is the short circuit current and the second is the output impedance. By the way, this current source is not there, right. In the AC small signal, this DC current source can be thrown out. Okay. So, we are going to do, what do you want to do first, short circuit current or output impedance? Do you want to do the output impedance first, short circuit current? Okay. Let us do any one, it does not really matter. Let us do the short circuit current. Okay. So, for the short circuit current, we are going to apply a voltage at the input and we are going to short this output. And measure the current. This is the plan. Now, let us see, C3 is out, it cannot take any current anyway, it is useless, both sides of C3 are at ground. So, C3 is not going to come into my equations at all right. So, we do not have to worry about C3. What about C1? C1 is going to take current, but this is some private loop between the voltage source and C1, right, a loop of its own, right. The current through C1 is well defined, it is just coming from this voltage source, it is a loop of its own. This current has nothing to do with this short circuit current, all right. So, whether C1 is there or not, it really does not matter, it is not going to come into my equations, fine. So, let us forget about C1. So, all I have right now is C12 and C2. Okay. So, C12 seems like it is providing some additional path and C2 it looks like it is changing something over here, something is going to change. Let us see what happens. So, first we apply our voltage V in and then that creates a current Gm times V in. Gm times V in can now choose to go between many different paths. Okay. So, this is Gm times V in, Gmb times V in is anyway out. There is an RDS, there is now a C2, there is also a C12 and there is the impedance looking into the source of M2. Now, the impedance looking into the source of M2 is unchanged from the DC, right. In DC whatever you had computed, it is the same old stuff. alright, same thing, just that now there are two more competitors, there is C12 and there is C2, and we just have to work out what is the portion of current that goes into M2, into the source of M2. Fine, this is our setup. So, in other words, my setup is like this. Some Z, where Z is really 1 by GMB plus GM of device number 2, right, approximately, we know what that is. So, this is what I want to do, what I want to solve. Okay, I have simplified. So, I have my V in over here, this V in input source creates a current GM1 times V in. This GM1 times V in has to choose between the following paths, it has to choose between RDS1, C2, C12 and Z, and whatever goes through Z is my answer. Okay? My final answer is the current that goes through Z, that comes through Z rather. Fine, great. Now, looks like this C12 is creating a complication over here. It looks as if. What if C12 was not there? Would you have been able to write the answer by inspection? It is just that now the competitors are Z and RDS1 parallel with C2, right. You could combine RDS1 and C2, write them in parallel and then write out this expression. So, this is now going to become RDS1 in parallel with 1 by SC2, this is going to be RDS1 in parallel with 1 by SC2, the rest of the stuff is going to remain the same, and that will be your answer. Okay. So, if C12 had not been there, this is what would have happened. You could also say that C12 is almost with respect to ground. Suppose you think that C12 is with respect to ground, right. Imagine you are doing superposition, this is not right, it is not right. Okay, do not do superposition, it is not right in this case. Imagine you are doing superposition, GM1 times V in current, and then you do this experiment once. So, C2 and C12 come in shunt with each other, and then later on you are going to just apply V in and check the same answer. Okay. Can you do such a thing? So, technically you can't. However, if you specify the value of this current, you can. So, instead of drawing a diamond, if you draw a circle like I have drawn and you say that this current source is GM1 times V in, now you can do superposition to find out this current. These are now two independent sources, one source is GM1 times V in, the other source is just V in. Okay. So, you can actually do superposition, in which case what is going to happen? I apply GM1 times V in current over here and then find out what is this current, and that is going to be the same expression, but here instead of RDS1 I will write RDS1 in parallel with 1 by S C2 plus C12. Fine, done. The second experiment is that I apply V in. Now, I do not apply this, This current source is no longer there. I just apply V in and see what is the current going into Z. All right. Now, that is going to be a little harder. Fine, you could do that. Another possibility is to just do a short KCL. Okay. In this particular case, the short KCL is going to work to your advantage, right. It might work out faster. So, you look at this circuit, you say that I do not know this voltage V, let us say this voltage is V. Okay. So, the KCL is like this: V by RDS 1 or rather V times GDS 1 plus V times SC 2 plus V by Z, okay, plus V minus V in times SC 2 is equal to 0. Okay, this is your short KCL, and from this KCL your V in is going to come on this side, everything else is proportional to V. C12, thank you. Okay, so V in times C12 can be moved to the other side, and therefore, now you know what is V. Thank you. Thank you for pointing out there was a major. Okay, so GM1 goes to the other side. So, this becomes minus fine. So, now I have got V, and guess what, this current is just V by Z minus V by Z in fact. Okay. So, my short circuit current is V in times 1 by Z, and what is Z? We have forgotten what is Z. Z was this complicated thing, all right. You can, I mean, in this particular case you can write the whole thing, it is not too hard. Let us call this, this is annoying, okay, let us call this GM2 prime, all right. That extra bracket looks funny to me. Okay, so, just let us write it as GM2 prime. So, Z is nothing but, okay, so I will do it on the next page. So, transconductance. Okay, so, the transconductance is minus, because I am looking at the current coming in. So, therefore, a minus times V in goes away in the transconductance expression. This is the expression for V, I was looking for V by Z, all right. So, SC12 minus GM1 divided by Z times the denominator. So, GDS1 times Z plus SC2 times Z plus 1 plus SC12 times Z. Okay, so, this is the short circuit transconductance, and Z I will plug in as RDS2 by 1 plus GM2 prime RDS2. Okay, where GM2 prime is understood to be GM2 plus GMB2. And now what do I do? I have got this okay. So, the easiest thing to do is to multiply numerator and denominator by 1 plus GM2 prime RDS2. Fine. This is how it is. We do not like things in this complicated fashion, right. We would like to take the DC term out. And what was the DC term? The DC term looked like this. Okay, maybe the DC term deserves a little simplification. So, the DC term was GM1 RDS1 in the numerator times 1 plus GM2 prime RDS2 divided by RDS1 plus GM2 prime RDS1 RDS2 plus RDS2. Okay, this was the DC term. Fine. Now, this DC term has to be taken out. Look over here carefully. GM1 RDS1 1 plus GM2 prime RDS2. 1 plus GM2 prime RDS2 appears straight away. GM1 is right over here, and an extra RDS1 has to be taken out, 1 by RDS1, or rather RDS1 has to be, this is wrong, no, this is fine, this is correct. Why is this correct? The numerator has dimensions of 1, denominator has dimensions of resistance. So, transconductance should have dimensions of 1 by resistance, Siemens. So, just quickly check the units, right. We need to take this portion out. We also have to take out GM1 from the numerator, and then what remains in the numerator? 1 minus SC12 by GM1. Okay, and that is very nice because it starts with a 1, right. There is no the coefficient for the term without an S is only 1. And then from the denominator you have to take out the DC term. So, in the denominator I have got RDS2 GDS1, which is DC, this is S, these two are S. So, that is not DC, 1 is a DC. So, I have got 1 plus GM2 prime RDS2 GDS1 GDS1 is annoying. All right, I think we have to multiply numerator and denominator by RDS1. Okay. So, that is why there was a slight inconsistency. Okay. So, I have taken out RDS1 from the numerator as well, and now from the denominator I need to take out RDS2 plus RDS1 plus GM2 prime RDS1 RDS2. Okay. And when I do that, I am left with a 1 at DC, because I have taken out RDS2, RDS1 and this whole thing, right. So, if I take that whole thing common, then all I am left with is a 1 plus S C2 plus C12 times RDS1 RDS2 divided by whatever you forcefully took common, right. You had taken something common forcefully, it was not really common. So, that has to be divided. Okay. So, this is the template. It looks awful, but this is where we are going to stop and declare victory. We have identified a 0. Is this 0 left half plane or right half plane? This is a right half plane 0. Okay. And a right half plane 0 is expected whenever you have stuff like this. Okay. This annoying gate to drain capacitor has created that right half plane 0. See C12, you see it is just C12, the location of the 0 is GM1 divided by C12. Okay, that is the location, the frequency at which the right half plane 0 is, it is at GM1 divided by C12. Okay. So, if C12 had been 0 for example, then this would have been at infinity, basically it would not have been there. Okay. Next we have got a pole, there is a left half plane pole which is very nice, simple pole on the real axis, negative real axis. Okay. C2 plus C12 times RDS1 RDS2 divided by a gigantic resistance. Check the dimensions, check that this is indeed S times a time constant, S C R, is it? It is R times R divided by R. Okay. So, the dimensions are that of a resistance, fine. So, this is it, I have got my 0, I have got my pole and I have got the DC term out, all right. So, this is where we stop dealing with the transconductance, this is the short circuit transconductance. Next we have to find the output impedance, and to do the output impedance I am going to connect the input to ground. Okay. And when I connect the input to ground, remember I had 3 capacitors. One was C12, one was C2, I had C12 and I had C3. Okay. So, C12 is going to now come in shunt with C2. So, instead of writing C2, you can write C2 plus C12. Fine, this is easy. C1 does not matter anyway, because it is now grounded on both sides. Okay. There was a C1 over here, that is now shorted, grounded on both sides. So, it can't take any current. All right. Now, we have to find the output impedance of this. Output impedance of this is 1 by SC3 in parallel with output impedance looking into the drain. Okay. So, it is just SC3, 1 by SC3 is just the extra stuff. Let us do that later. Let us place that parallel piece later on. What else is there? What else is there looking into the drain? It is the same formula. The source is now terminated with RDS1 in shunt with C2 plus C12. Instead of being terminated just with RDS1, now you are terminated with RDS1 in shunt with C2 plus C12. And let us see if we can write the expression by inspection. So, by inspection, the expression is going to be intrinsic gain of MOSFET number 2, which is GM2 prime RDS2 times, this is the intrinsic gain of MOSFET number 2, times what is on the source. What is on the source is RDS1 in parallel with C2 plus C12. Fine, I have written by inspection. This is the first term plus RDS2 plus whatever is on the source. Okay. Is this done? This is it. This whole thing comes in parallel with C3. So, you can write it as this divided by 1 plus this times SC3. Okay. This is the complete expression. Of course, we are not happy with this kind of an expression, we have to simplify. We have to simplify to a point where we can take the DC term common outside, and we know what our DC term was. Our DC term was just this, all right, GM2 prime, this was GM2 prime. GM2 prime RDS2 RDS1 plus RDS1 plus RDS2. Okay, that was our DC term. So, we are only going to simplify till that point. Now, what do we do? First thing we can do is multiply numerator and denominator by this portion, okay, by this portion. Fine. So, if you multiply numerator and denominator by that, you get I have a feeling I am making a mistake. I am, right. There was an RDS2 inside this, which I seem to have forgotten. Yeah, okay. All right. I have done all the multiplications also in the denominator. All right. Now, the first thing you see is that this is the DC term in the numerator, okay, and you can safely take this common outside. And when you take this common outside, this whole thing is left with a 1 and then plus S C12 plus C2 RDS1 RDS2 divided by that DC term. So, it is 1 0 in the left half plane. Sorry, I forgot to write the DC term. RDS1 plus RDS2 plus GM2 prime RDS1 RDS2. This is the DC term. This whole thing times 1 plus S C R. Okay. Dimensions are correct. S C R. This is the numerator, and in the denominator I have got 1, which is the only DC term, plus S times C2 RDS1, C12 RDS1, C3 RDS1, then C3 GM2 prime RDS1 RDS2, RDS2 C3 RDS2, plus S squared C3 C12 plus C2 RDS1 RDS2. Okay, so it is a second order denominator. Numerator is first order, denominator is second order. And I am sorry to tell you that if you try very hard to factorize, you will not be able to factorize this. Okay. Trust me, you can't factorize this. You can do your Sridharacharya equation and you know you will end up with some nightmare, but no need, you can't do it. All right, what is the point? Why did I do all of this if you can't do it? So, one important observation, your transconductance had a right half plane 0 and a pole, these two. This was your transconductance expression. Okay. DC term, right half plane 0, pole. Okay. The output impedance, the surprise has the same pole, has the same 0 as this pole. Okay. They cleanly cancel out. The 0 of the output impedance cancels out with the pole of the transconductance. So, the transconductance effectively provides only this 0, right. The pole of the transconductance will cancel out with the 0 of the output impedance when you multiply them together. Okay. The overall poles are contributed only by the output impedance. So, if you work out only the output impedance, right, if you look at the output impedance and work out just the poles of the output impedance, you know the poles of the system. If you work out the transconductance 0, that gives you the 0 of the system. Okay. So, let us think of it this way. Instead of doing all of this, you could have tried to find poles from output impedance RHP 0 from transconductance. Okay. And anyway you know the DC quantity, right. By the way, look at the DC quantity also, there is something interesting in the DC quantity also. This denominator cleanly cancels out with this, right. Even in the DC that some little bit of magic is happening. This quantity, this DC term cancels out with this denominator, which means you only need the numerator from the transconductance, and that is your answer. Overall voltage gain at DC is just this much coming from the numerator of the transconductance. You do not even have to look at the denominator cancels out with the output impedance. Okay. So, that is also something interesting. In any case, let us assume you know the DC stuff, the DC stuff is easy to do. Okay. Then after doing the DC stuff, you look at the output impedance and work out the poles, just the poles. Okay. If we had a shortcut, to find out just the locations of the poles, all right. And if we had a shortcut to find just the location of the RHP 0, then I can just write out the whole expression. Okay. So, this is the plan. Is it possible to do such a thing? Can I find just the poles from Z out, just the 0 from the transconductance, and write the rest of the stuff by inspection? The answer is, it is possible to do such a thing, we just have to know how to do it correctly. All right. So, let us stop here and we will continue in the next class.